Good evening, dear students, and welcome back again to this amazing course and challenging course of robotics engineering. Tonight, we will discuss a new topic of minimal representation of orientation. Okay, this topic we will try to minimize the representation of the orientation. So instead of using 9 elements of rotation matrix, how we can try to reduce this matrix to just 3 variables. How we can use 3 variables to represent the orientation of any rigid bodies. Okay, and these 3 variables are the rotation around x-axis and the rotation about y-axis and the rotation about z-axis. The combination of this rotation in any order, okay, or any combination of this in any order, okay. And because here we have a combination of 3 sequence of rotation, so it is appeared that this topic is based on the previous topic of compound transformation. Okay, so firstly, let me make a review for a composite rotation matrix and give you a solution for the previous homework of how to prove the pre-multiplication case for the rotation for the compound rotation matrix, okay, around the current rotation matrix, and also around the fixed about the fixed rotation matrix, okay. And the post multiplication for the case of the sequence of rotation matrices that rotate in each stage around the current rotation matrix, okay. The current case with respect to next, the current means it's the previous rotation matrix with respect to next rotation matrix. And in the pre-multiply case, any of the new rotation matrix is rotated around the old and the fixed rotation matrix of x, y, z axis of the x, y, z axis, okay. Okay, so how to prove this? Because it is appeared that the post multiplication and pre-multiplication, with post multiplication and pre-multiplication, we can use this principle also for minimal representation, because the minimal representation contains a combination of the rotation matrices around x, y, z. Okay, in order to prove, so here we have 2 methods to prove them, okay, especially for the case of pre-multiplication. But here I will show you the simple method, okay, and brilliant method which is based on the principle of the representation of rotation matrix. Here, as we said before, we have three cases to that we can use a rotation matrix. The first case, as the orientation of rigid body with respect to reference frame r of 0. The second one, okay, the change of coordinates from frame to frame. The last one, the rotation operator on vectors. Okay, as we can see here, because the change coordinates, the new coordinates is almost with respect to previous one, or to the current, one. So RFC is rotated with respect to the previous or the current rotation matrix. So we can use this formula to prove the post multiplication case. And here we have a vector v. The new vector v dash is rotated around the fixed axis. Okay, here v dash. If I also make another rotation, v double dash, it also rotate around the same axis. So we can use this representation to prove the pre-multiplication case. Okay, nice. Okay, so let me prove this in a nice whiteboard, as we did in the classroom. Okay. Okay. So here you have a nice whiteboard with nice pen with multiple colors. Okay. In order to make everything clear. Okay. So if you start by writing the first coordinate, okay, for example, here we have x, here we have y, here we have z. Okay, and for example, here we have here any vector. Okay, for example, any vector here. Any vector, I call it as B to represent this vector. Okay. Also, if we make a rotation matrix for this frame, for example, around x-axis, for example, we have this frame here, this new frame, for example, we call this, for example, x2, we have z2, we have y2, and call this as y1, x1, z1. Okay, so the first step, I have this vector b. Okay, here we have this vector, B. If I want to represent, if I have this vector, for example, in frame 2, and I want to represent this with respect to frame 1, okay, so just I write B, B1 equal, okay, B1 equal the rotation matrix. For example, here it is around, it's around here X, can call it X, or we can call it as R21 also, or R21, B2, okay. So because this vector can be represented in frame 2 or in frame 1, okay, nice. So here we have this vector B1 can be represented with respect to the vector in another frame, in the next frame, okay, nice. If we make another rotation matrix, okay, for example, yeah, you can choose it to be, for example, around for the new rotation matrix, for example, around the y-axis, around the y-axis, okay. If you make, for example, a rotation around this y-axis, okay, the y-axis will be fixed, the y-axis will be fixed, but the x, here we want to make a rotation around, for new frame, around y, the new y-axis, okay. So the x-axis will go down, so the x-axis we can, this is it, the x-axis can go down, the x-axis, the new x-axis, here the similar y, the y is constant, not rotated, okay, but the z-axis, the z-axis will rotate a little bit, okay. Yeah, if I want to draw it, here it is, the y, you can call it y3, the y3, x3, and here the z3, for example, z3, okay, the z3. We make a rotation around the y-axis, so the new if I want to represent, okay, this P3, I want to find B2 with respect to B3, okay, so just I will multiply B3 with the new rotation matrix Ry, and this rotation matrix is around the current or the previous the same rotation matrix, okay. the ry is around the second frame, okay. The new frame, the frame 3 is rotated around frame 2, the current frame, or the last frame, or the previous frame. The same is the similar, okay, but it was not rotating around the fixed frame or the old frame, frame 1, okay. So we can call this as 3 2, okay. If I want to make a compound rotation matrix, okay, example, if I want to make a compound rotation matrix, for example, if I want to find B1, okay, if I want to find B1 with respect to B3, I have to replace B2 here in the equation 1 with B2 of equation 2, and I will get Rx or R21, okay, it's the same, multiplied by R Y, okay, multiplied by R Y or R3 to B3, okay. Just I replace B2 with all equation 2 term, okay, and here we get the post multiplication. The first rotation matrix are Rx multiply post multiplication with Ry, okay. So here we have B1 equal B3 equal Rx Ry B3 post multiplication, okay. So yeah, just we prove the most important formula for post multiplication, okay. Now let us prove the second formula for post multiplication, okay. So just we have to erase everything here in this screen, okay. In order to make this screen very clear, okay. Now we will use the concept of Pareto and vector, okay. Here we have this fixed frame X, Y, Z, the same frame. We will not write any new frame, okay. Just all of the rotation will be around this frame. It is so simple, okay. So simple, but it is previously it appeared as a so complicated problem, okay. And here we have this example, call it example V1. Firstly, we will make a rotation around x-axis. Here this the first rotation around x-axis v2, okay, and the new v2 equal the rotation around the x-axis multiplied by v1. We can call it as this the first rotation, okay. Also we can call it r2, okay, rotation from 1 to 2 position. Now if we make another rotation for v2, but this time, for example, here we have this around x, for example by theta around x axis, we can make a rotation, for example around z axis, for example, okay, just you can move this here around z axis, okay. I can make a rotation around z axis to be v3, for example. v3 equal rz or 3 to v2, okay. So if I want to find v3, for example, if I want to find v3 with respect to v1, just I will replace yeah, we will replace v2, all the term here of v2 with v2 here, okay, with this v2, okay. Just we will write r v3 equal rz multiplied by rx multiplied by v1, or 32 r32 r21, and here we have a pre-multiplication because the first rotation around x, then around z. So here we have a pre-multiplication because any new rotation will be pre-multiplied with the previous multiplication. And here now we have finished the proof for this formula, for the two formulas for pre-multiplication and post multiplication, okay. Coming back to our slides, slide number 56, okay, to resume the minimal representations. So it is similar to the case of the rotation of angle 3 around the last axis, then around the second axis, and around the first axis, okay. We will see this later on. So we have 12 sequences are different or are unique. We have 12 unique formulas, okay. Let's start, or let us start with how to verify the 6 conditions. The 6 conditions for unity or unitary conditions. If we take any vector here and take the square root for this summation, we'll obtain the one for the summation for the square for each element. We'll obtain one with the norm or the amplitude of the vector equal 1. If we make a cross product between any of two vectors, any two different vectors, we will obtain the cross product. With the cross product we will obtain the third one, but with dot product we will obtain the zero value. Okay, so now again we have important question. The rotation matrix representation needs 9 elements to completely describe the orientation of a rotating rigid body. Any easy way? We have 9 elements. Yes, we have an easy way for Euler angles representation, a rod pitch yaw representation. Okay, so here we have 3 angles: phi, theta, psi. Okay, other references uses, for example, alpha, beta, gamma. Alpha, beta, gamma. Okay, here we have a common angles or cases or common combination of rotation. Euler angle 1, and the rotation always the first axis is fixed. Okay, in all cases, because we rotate around the first axis. Okay, phi around z, then around the new or current axis. U means x, zx, w means the z axis for new frame, zxz. Okay, then or zvw means zy, zy dash, z triple dash. Okay, also, or for rod pitch yaw, you have the rotation around x, y, z. And because as we said before, the case, okay, the rotation around the fixed axis is similar to the opposite case of the rotation of the inverse order for the case of the rotation around moving current axis. So you can use the formula of rod pitch yaw to find, for example, the cases for xyz, for xyz, for zyx. Okay, for Euler angles, and later on we will see this in MATLAB, how we can use the rod pitch yaw formula to find the zy axis, the zyx Euler angles or Euler rotation. Okay, so here we can prove, we can find the formula by using our proof for post multiplication. Okay, here we have, for example, okay, here we have the first rotation around the z-axis, around the z-axis. So here we will get a new frame, x dash, y dash, z dash. Secondly, we will rotate around this new, this current, okay, this current frame x dash, okay, to obtain z double dash y double dash, okay. And this also is considered as previous frame with respect to the last this third frame, okay. The rotation around x, we have rotation around x rx dash. Finally the rotation around, again around z, but around the z axis of the current frame around z double dash, okay. We will obtain x double dash y double dash and z double, we will obtain z triple dash y triple dash, and the z triple dash is equal to the z double dash, okay. You have r z double dash, and because here we make a rotation around the current frame, so just we will use the post multiplication formula. So the compound rotation method will be rz multiplied by rx dash multiplied by rz double dash, okay. Rz rx dash rz double dash is the order of definition in concatenation, okay. If we make a multiplication, we will obtain this formula, and as we said before, c means cosine and s means sine. This to simplify the symbols here. For example, given vector v double dash expressed in this frame, its expression in coordinates of rf is, okay, just we multiply the compound rotation matrix with v triple dash to obtain the v, okay. The orientation of rf is the same that would be obtained with the sequence of rotations for the case of fixed, okay. For the case of fixed, just we will reverse the order around z, okay, around z with the same angle, yeah, psi, then theta around x fixed, and then phi around z. And we will see also the proof for this, and this proof can also used to prove the pre-multiplication formula in general, okay. Here we have this, the direct problem. If I have the angles, what will be the rotation matrix? Yeah, in this case, if I have the rotation matrix, okay, what would be the angles, the theta and alpha and psi and phi and phi, okay. So just by inspection here, just we can use by using simplification formulas, okay. For example, it is easier to start by theta, because here we have cosine theta r33, okay. And here we have sine theta, but here we have sine psi and cosine psi. If we make a summation for the square for each element, we will obtain, because s sine square plus cosine square is equal 1, so we'll obtain sine square theta, and here we have cosine theta. As we know, the tan equal sine over cosine, okay, sine over cosine, okay. So the tan inverse, with tan inverse we can obtain the angles, okay. But in order to obtain exactly the location, okay, because the tan inverse just give us the angles, okay, between minus 90 degree to 90 degree, and if I want to find the exact location for the angle in three exactly in the frame, okay, in x y axes from 0 to 360, we have to use this formula, okay, and I will show you the principle of this formula 8 and 2, okay, 8 and 2, because here we have a square root for this term, this term for sine, this the term for cosine, okay. It is like tan inverse, but 8 and 2 you will find exactly the angle of the theta, okay. If the cosine, if this term is not equal to 0, means if the sine is not equal to 0, okay, because here we make a division by sine theta, okay. So the second step, we can find the angle of psi, the angle of psi, and the angle of psi is equal to this term divided by sine theta, and sine theta is obtained from the previous step here, okay. R31 over sine theta equal sine of psi, and here we can get the cosine of psi, so the psi equal the 8 and 2 sine psi over cosine psi. Similarly, we can find the y from here, y. Here we have sine y, here cosine phi, and sine theta is obtained from the step 1. So y equal 8 and 2 r13 over sine theta minus r23 over sine theta. There is always a pair of solutions, okay, because the psi and y depends on theta, and theta has two solutions, plus or minus, okay. We have a pair of solutions in the regular case. They are always singularities. The meaning of singularities, that means the non-regular case. The regular case, we have two solutions. If we have other than two solutions, zero solution, one solution, three solution, and so on, is singularities. It is a non-regular case, non-common case, okay. For example, if theta equals 0 or equal plus minus pi, because we make this term equal 0, okay. If this is the case, just we can obtain the sum phi plus psi, or the difference can be determined. Here we take a look of the importance of 8 and 2 function, and the difference between 8 and 2 and the tan inverse, and how we can calculate by our hand the output of 8 and 2, okay. The 8 and 2 takes values in minus pi to plus pi, so it will cover all the range, okay, for xy axis from 0 to 360 degree. Okay, instead of the output of arctan, the output values in between minus pi over 2 plus pi. Okay. In order to understand very well the relationship between a tan 2 and tan inverse, just look at this graph here. Just look at this graph. Okay, and as we know, the tan inverse, the input for tan inverse is sine over cosine or x over y. For example, if the x value is 5 and y value is 5, okay, the tan inverse here at this point, in this case, the x or sine is positive and the y or cosine is negative. So the output of tan inverse is, with the calculator, 45. Okay, for example, here this is the case 45, and you can compare this the first case, x greater than x greater than 0 for this case and this case. In this case, tan inverse 5 over 5, 45, tan inverse 5 over minus 5 equal minus 45. Okay, and this is similar to the real output of the position of this vector. Okay, this vector is located in 45 and this vector is located in minus 45, because the x-axis is used as a zero reference. Okay, as a zero reference, and and each angle will be calculated with respect to this zero reference. Okay, the x-axis is used as a zero reference. Okay, the other case of x, if the x is less than 0, it's a negative value, like here. X is less but y is greater. Okay, if you use a calculator, we will obtain minus 45. It's minus 45, but the angle, it is in the second quarter. Also, if you remember from the secondary school, all cases, okay, any angles here in this first quarter has a positive sine, positive cosine, positive tan. Okay, but here it has just a positive sine, but it has a negative cosine, negative tan. In the third quarter, we have just a positive tan, but negative cosine and negative sine. And the last case, we have just a positive cosine. Just with this case, any angles here. Okay. Okay. As a correction, the y represents sine and the x represents cosine. Because the x is in neighborhood to the angle, whereas the y-axis is in front of, okay, for the angle. So y represents sine. The sign here is positive, sine, positive. this case, and the cosine here is positive. Okay, okay. So if for this case the x this the y x is less than x less than 0 and y is greater than 0. In order to find this angle, the angle is equal to the angle is equal to by or 180 degree plus minus 45 or plus arctan plus the result of arctan by plus the result of arctan. Okay, similarly for this case, x greater than 0, x is greater than 0 but y is less than 0, y is negative. Sorry, for this case x is less x is negative and y is negative. The output of tan inverse is 45, but this 45 in the third quarter. Okay, and because the output is from minus pi to pi, then and it is calculated with respect to x-axis as 0 reference. So just I have to find the angle here. The angle is equal to pi minus 45 or pi or minus pi, sorry, minus pi, because this angle in the opposite direction, in the clockwise, when the angle is in clockwise direction, the sign of angle will be negative, minus pi plus 45, okay, minus pi plus arctan. In this case, x equals 0, but y positive. Exactly, this is, and in easy way, this is equal 90 degree or pi over 2. If y is negative, the angle, that means the angle here in this direction is equal minus pi 2. If x equals 0, y equals 0 is undefined case. Okay, now let us move to the next slide, the next subsection for this lecture today, the roll, pitch, yaw angles. And in this case, we rotate around the original or old fixed axis, the x, y, z. Okay, so yeah, the first rotation is around the x-axis by psi angle. And so here we have a new frame, x dash, y dash, and z dash. Okay, this is a rotation rx psi. Second, we will make a rotation for this new frame, but with respect to the fixed frame, the old frame around xyz. Okay, and now we obtain the x double dash, y double dash, z double dash rotation with angle theta around the fixed frame xyz. Okay, around the y-axis of the fixed angle. Okay, r y. Okay, lastly we make a rotation around the z-axis of the fixed axis. So we rotate the double dash frame around this z-axis, the old z-axis, by angle of phi to obtain the triple dash axis. At the triple dash axis, x triple dash, z triple dash, and y triple dash. And here we can see the RZ phi. Okay. Here we have C1 T. We will see just in order to prove the concept of pre-multiplication. Okay, because here we will use the principle of post-multiplication to prove the pre-multiplication. Okay. For example, here we will use the principle of post-multiplication. Okay, just in order to use the principle of post-multiplication, firstly I have to rotate with this C1. C1 means I have to return back to the z-axis, then make a rotation around y, then invert this C1 movement. Okay, just in a simple way. Okay, just in order to make to use the principle of post multiplication, I have to rotate around the current axis. Okay, so in order to rotate around current axis, I just to make this modification. Okay. Similarly, C2 means I have to return back to invert everything. Okay, and make a rotation around Z, just and then invert this C2 movement. Okay, C2 means I have to return all the new movements to be aligned with Z axis, the old Z axis, then make a rotation around Z, then cancel any of these modifications. Okay. Also, in all pitch yaw angles, we have a direct problem and inverse problem. Direct problems means if we given the psi, theta, y in this order, okay, not the order. Here we have a pre-multiplication. We prove this pre-multiplication. That means firstly Rx psi, then pre-multiplied by Ry theta, pre-multiplied. We prove this with pre-multiplication previously. Okay, but also this technique is also used to prove the pre-multiplication. Here we use a post-multiplication to prove the pre-multiplication scenario. Okay, just if we make a multiplication for these rotation matrices, we will get this big formula. The inverse problem, if given the rotation matrix, we have to find these angles. Okay, so also you can use the previous, please check this formula. You can use the previous formula and also check the singularities cases when the theta is equal to plus or minus pi over 2. Okay. we said before, here this rotation, the order of definition is a pre-multiplication, okay? Rx, Ry, Z need to refer each rotation in the sequence to one of the original fixed axis. So here, use the angle axis technique, the same technique that we use to obtain the angle axis formula for each rotation in the sequence. Okay, we just go back, okay, to make alignment with the fixed axis, make a rotation, okay, the needed rotation around the fixed axis, then invert any previous or any made movement, in C by C transpose, with T being the rotation matrix reverting the previously made rotations. So C is reverting the previously made rotations to make our frame, okay, aligned with the fixed axis, go back to the original axis. So in order to prove this pre-multiplication, just we will use the post-multiplication technique. As we said before, the post-multiplication technique is the common formula, okay. Firstly, I have to rotate around X, no problem here. Then I have to rotate around Y of the fixed axis, but just in order to make everything around the current axis, I revert any previously made rotations. The only made rotation is around X, okay. I make Rx transpose to align our frame to the Y axis of the old frame. Then I will make a rotation Ry theta. Then I have to revert this movement Rx transpose. The inverse for this is Rx, okay. After that, I have to revert in order to make a rotation around Z. I have to align our frame to the old frame XYZ. So I have to revert any previous rotation, any previously made rotations. And here we have Ry and Rx, because I make two rotations, Rx then Ry. So in order to revert it, I have to multiply Rx transpose with Ry transpose Rz. So after that, I have to cancel this term. Just I multiply by Ry Rx. After that, if I make simplification for this long term, Rx transpose equal 1, okay. Rx transpose, yeah, Ry Rx multiplied by Rx transpose Ry transpose equal 1. So just we will get the final of Rz pi Ry theta and Rx psi, and this is equivalent to this term, okay. Now we will get some examples, and in order to gain more understanding for this topic, okay. For example, frame B was initially coincident with A. We then rotated this frame about XA axis by 30 degrees. Then we rotated it about YA axis, so it is fixed, yeah, by 45, then about
rotate axis by 60. Note that X, A, Y, A axis are the original axis of frame A. Calculate the result. The resultant rotation matrix RBA. So just we make a pre-multiplication. The first rotation Rx pre-multiplied by Ry, pre-multiplied by Rz. Just please check these calculations. Okay. As you said before, some references use alpha, beta, gamma, like the reference of introduction to robotics engineering of Craig. The author of this reference is Craig. It is a useful reference, and this reference uses alpha, beta, gamma, okay, as angles, alpha, beta, gamma, alpha for z, beta, okay. So in order to not make any confusion, because these examples can be found in this reference also. Let's make a comparison. You will find everything is identical. Everything. Here another example. Find x, y, z fixed angles for rotation, gamma, beta, alpha for the following rotation matrix. Just here we have to obtain these angles. Okay. Z, x, gamma, beta for y, alpha for the rotation around z. Okay. Check at home for x, y, z order of rotation. Can you find the same RBA given in the example by multiplying each rotation matrix in the following order? Okay. Rx 10, Ry 50 degree, and Rz 20. Okay, here we make inverse problem. Here we want to check our problem by direct formula. Okay, now we reach the end of the theoretical part for this module of the spatial or the spatial transformation for the rigid bodies. Thank you very much for your time, and I would be very happy if you have any question. The next lecture we will use a MATLAB, okay, to gain some practical knowledge and experience with this nice simulation tools. Okay, thank you very much.